Welcome to my presentation on the Baltic Sea environmental assessment using indicators. My name is Sarah Piehl and I'm working in the Coastal and Marine Management Group at the Leibniz-Institute for Baltic Sea Research in Warnemünde, Germany. Within this video lecture, I will give you an overview about environmental assessment and indicators and how they are related. A focus will be on the eutrophication assessment and indicators as an example to assess the state of the Baltic Sea. Finally, I will use oxygen as an example to go a bit more into detail about the strengths and weaknesses of indicators. Increasing human-induced pressures on the environment, as for example littering, call for urgent management of human activities. But understanding and managing complex systems, such as the society or the environment, requires simplification. Essential to this is to create a simple picture with a limited number of factors, which is achieved by indicators. Indicators are, for example, used to measure progress towards the sustainable development goals, which include environmental goals alongside social and economic goals. Here, they provide a useful tool to assess the state of the environment and trends, and thus to support the sustainable development. Indicators are often combined into summary values, such as the Baltic Health Index, one number which serves as an indicator to track the health of the Baltic Sea. Such summary indices help to reduce the overwhelming amount of information and thus to see the bigger picture. So indicators are useful tools that facilitate a simplified view of complex systems. Generally speaking, an indicator is a measurable metric that provides key information on a status and trends. In context with management issues, indicators are used to measure specifically progress towards a goal, which is a future condition which you would like to achieve. So indicators answer the following basic questions. Where are we? Or what is the current environmental status? How far are we from our desired goal? And which way are we going? Are we approaching the goal, or is the situation getting worse? Considering the health of the Baltic Sea, those questions are answered by regular monitoring and assessment activities carried out by the Helsinki Commission, HELCOM. HELCOM assessments provide an overview of the status of the ecosystem health for the Baltic Sea area at a given point in time. In this figure, the summary of the last assessment for biodiversity indicators and pressures is shown in relation to the Baltic Sea area as percentage of square kilometers on the x-axis. For most of the biodiversity indicators and pressures, the results are based on multiple indicators, as for example for eutrophication in the first line. But results can also be based on a single indicator, as for example commercial fishing. As can be seen by the dominating red colors in this figure, for most of the assessed indicators, the status was rated at poor for most of the Baltic Sea area. The poor environmental conditions of the Baltic ecosystem are caused by the way and the intensity with which we use the Baltic Sea, its catchment area, as well as its marine resources. For the Baltic assessment, the following 7 major pressures are considered: inputs of hazardous substances, species removal by fishing and hunting, inputs of underwater sound, for example from offshore activities or shipping, inputs of marine litter from land and at sea, eutrophication through excess inputs of nutrients, the introduction of non-indigenous species, as well as seabed loss and disturbance caused, for example, by dredging activities. In the following, I will focus on eutrophication as an example for an indicator-based assessment. But first, a short description of the eutrophication symptoms in the Baltic Sea. Eutrophication means the enrichment of aquatic systems with nutrients and a subsequent increase in phytoplankton productivity. It starts with excess inputs of nitrogen and phosphorus into the system and potential changes in nutrient ratios. Direct effects are enhanced phytoplankton or algae growth, which is expressed through increased chlorophyll A concentrations in the water column, changed phytoplankton community structures, favoring cyanobacteria or so-called blue-green algae, and the growth of short-lived macroalgae. Furthermore, sinking dead algae lead to reduced water transparency. Indirect effects include oxygen depletion, where oxygen consumption at the seafloor is increased through decomposition of dead algae. In the worst case, oxygen depletion leads to mass mortality of benthic animals or fish. These changes may in turn affect species composition and food web interactions in the long run. Eutrophication affects the Baltic Sea at different levels. Likewise, the eutrophication status is assessed by multiple indicators within 3 criteria which reflect the symptoms of eutrophication. The pie charts show the integrated results for the 3 criteria: nutrient levels, direct effects, and indirect effects. The map in turn shows the overall eutrophication assessment, integrating the 3 criteria. As can be seen in the map, the Baltic Sea is divided into different subbasins, which is done to account for different conditions in, for example, biology or hydrology. And, as can be seen again by the dominating red colors in the map, in terms of eutrophication, about 97% of the Baltic Sea area is rated to be in a poor condition. In this figure, the single indicator results are shown exemplarily for 5 subbasins. For the criteria nutrient levels, total and dissolved nitrogen and phosphorus in the surface water are monitored. To assess direct effects, phytoplankton production is measured through the chlorophyll A concentration in the surface water, and further water transparency and the extent of cyanobacteria blooms are monitored. To assess indirect effects, the indicator oxygen depth is used, which estimates how much oxygen is missing from the Baltic Sea deep water. And one biodiversity indicator is currently used in order to address effects on species composition of benthic communities. What can further be seen in the figure is that not all indicators are applicable in all subbasins, which is indicated by missing circles, and that for some indicators no information is currently available, as a commonly agreed method is missing, which is indicated by empty circles. Indeed, indicator development can be a long process, as indicators need to be well planned, to be appropriate to local conditions, and meet the highest possible quality standards. But more importantly, indicators need to be selected on several criteria, as for example, linkage to anthropogenic pressures, measurability with monitoring data, and ecological and policy relevance. Now having a look again at the indicator assessment results, how do we actually know if a good status for an indicator was achieved? By evaluating the observed status of an indicator against a threshold value. Threshold values can be a range or maximum-minimum values, as been indicated in the upper graphs, as well as data trends, as shown in the lower graphs. Threshold values can vary between subbasins for a single indicator to account for the differences in local, biological, and hydrological conditions. In such a case, a harmonized threshold value setting approach is crucial. Finally, the outcome of an indicator evaluation is expressed in terms of achieving or failing the threshold value, and thus determines if a good status is achieved or not. So how exactly are threshold values obtained? In the most simple approach, one could use an existing undisturbed site, as for example a marine protected area. If sufficient historical data is available, one could go back in time and identify periods before the indicator value changed significantly, which is known as change point analysis and exemplarily shown in the figure with volume-specific oxygen depth on the y-axis and a time series on the x-axis. Here, the turning point around 1945 would be the identified change point and used as threshold value. Another approach includes numerical ocean models, utilizing hindcast model simulations, and comparisons with the earliest available data. Most important to understand is that the threshold setting approach is a very crucial step in any indicator development, again, as the assessment result is based on whether meeting or not meeting the threshold value. For the last part, I will use oxygen as an example to show you the strengths and weaknesses of indicators. For the eutrophication assessment, oxygen depth is already used as an indicator by HELCOM to evaluate the lack of oxygen in deep waters with permanent hypoxia, meaning areas where vertical mixing with oxygen-rich surface waters is limited and where the oxygen levels drop below 2 mg per liter. By that, the indicator currently only assesses 9 out of 17 basins of the Baltic Sea area. This example shows very well that due to the local conditions, not every indicator is applicable in all areas of the Baltic Sea. Nevertheless, to use oxygen as an indicator in shallow areas, as for example the Western Baltic Sea, another oxygen indicator is currently being developed, assessing seasonally occurring oxygen depletion. Here, several Baltic states already implemented monitoring strategies in their national waters, but utilizing different approaches as well as threshold values for oxygen. In Germany, for example, 2 threshold values are used, depending on the mixing behavior of the water column. For the assessment, 5 annual measurements of near-bottom oxygen concentrations are taken per station. Thereof, the minimum value is extracted. And for an assessment cycle of 6 years, this data is then first temporally and then spatially aggregated. Thereby, the majority of stations in a basin which achieved or failed the threshold value decides on the overall assessment result of that basin, as shown in the map. On the distribution of the monitoring stations, indicated by the triangles and the dots, it can also be seen that with this approach, precise information about the spatial extent of oxygen depletion areas is not possible. Currently, there are 2 major limitations with all approaches. First, observational data is limited in both time and space. And second, not always the whole water column is monitored. So currently, observational data does not provide the spatiotemporal resolution needed for a highly dynamic indicator such as seasonally occurring oxygen depletion. But how to fill the gaps in the monitoring data? Numerical ocean models can provide high-resolution information, as for example, on the areal extent of oxygen depletion areas, further adding a vertical component to the analysis, allowing volume measurements, for example. In addition, with up to daily temporal resolution, information on the duration and repetition rates of oxygen depletion situations can be gained. So models help to extrapolate single-point measurements into space and time, as seen in this figure. However, any model is only a simplified representation of the real world, and thus, an integration with observational data is necessary to provide the most accurate information possible. An example of a pure model result focusing on the temporal aspect of oxygen depletion is shown in this map. Here, the average days per year where oxygen levels drop below 2 mg per liter in the near bottom water layer is shown, averaged for the period from 2011 to 2016. Black to purple areas indicate areas where oxygen depletion can be expected for more than a half year on average, and red areas indicate areas where oxygen depletion occurs for more than 3 months on average per year. So with this map, information on how many days a year oxygen depletion situation can be expected. But is this information relevant for benthic organisms? As the Baltic Sea naturally exhibits oxygen depletion, organisms may be adapted to low oxygen conditions. When oxygen concentrations decrease, some just may move away. Others may be able to reduce their metabolic activities. Further, different species may exhibit different tolerances to thresholds, durations, and repetition rates of oxygen depletion situations. So in order to develop a biologically meaningful indicator, the information on the duration and frequency of oxygen depletion situations for different threshold values is very important. At present, seasonal oxygen depletion as an indicator has still some weaknesses. Currently, there is no agreed-upon monitoring strategy. National concepts for seasonal oxygen depletion utilize different thresholds and assessment approaches. Seasonal oxygen depletion exhibits a high spatiotemporal variability, and due to limited in situ measurements, there is a lack of information on the spatial extent and temporal duration of oxygen depletion situations. A strength is that the indicator enables a wider application area than oxygen depth, which only assesses permanent hypoxia in deep basins. Oxygen depletion has a high ecological and policy relevance as it affects fish and benthic animal populations. In addition, seasonal oxygen depletion probably responds more rapidly to anthropogenic influences than permanent hypoxia, which is further influenced by long-term factors such as infrequent saltwater intrusions. Current limitations could be overcome with an integrated approach, utilizing both model simulations as well as observational data. This would allow to enable seasonally occurring oxygen depletion as a powerful eutrophication indicator. And on that point, I would like to conclude my presentation with a short summary. Environmental indicators are measurable metrics that respond to pressures acting on an ecosystem and that are used to monitor the status and trends of an ecosystem. Indicators link anthropogenic pressures to policy measures for achieving a good environmental status. Indicator threshold setting is a crucial step, as the goal of a good status is based on whether meeting or not meeting the threshold value. And finally, the validity of an indicator is only as good as the underlying monitoring data. Current subjects of research are to link more closely water quality indicators, such as oxygen, with biological indicators, such as benthic diversity. Moreover, to take climate change effects into account, considering threshold setting approaches and assessments. Considering current attempts for monitoring, a combination of model results, measurements, and remote sensing methods will enable a comprehensive environmental monitoring in future, which is increasingly needed as the world population continues to increase and therewith its demand on the environment. And with that, I would like to thank you for your attention.